Thank you for clicking on this video. This is our first physics video. We will talk about one-dimensional motion. We will restrict ourselves to one dimension. And what we will do, what will be our task? As object moves, its position is changing. So what we want to do, we want to derive the formulas in this video that we will be using to describe position of the object as time changes. First of all, definitions. Which definitions do we need? We need definition of acceleration, and we need definition of velocity. What is definition of acceleration? I write projection of acceleration on x. Remember vectors video? We work with projections. A sub x means that x in a given coordinate system, and in this case we will have just x since it is one-dimensional motion. I find projection of acceleration and velocity on x, and x is position of the object along x. Now, a sub x, by definition, is rate of change of velocity, derivative of velocity, projection x, I keep it here, dvx dt. What is definition of velocity? It is derivative as a function, it is derivative of position with respect to time. What I don't like in these formulas, the way I wrote them, I forgot to put here time. So this is definition of acceleration, and if time, as time changes, I can find acceleration, x component of acceleration, if I know velocity. And I can find x component of velocity if I know position. What I will do next, before I do anything, let's call this formula 1 and this formula 2. What I'll do next, I will take antiderivative of both sides of equation 1. Stay with me. Ax of t dt will be on the left. What will be on the right? I will have integral dvx dt. I take integral with respect to time. But what is antiderivative? It is function itself. So I get vx as a function of time plus constant. Now I know how to find velocity if I'm giving acceleration. I will add this formula here. So if I'm given acceleration, then vx as a function of time could be found as integral ax of t dt. I will skip this constant because this indefinite integral will generate a constant here that I will find from initial conditions that will be provided in the problem. Now what will I do next? I will take antiderivative of both sides of the second equation. Integral vx of t dt is equal to integral dx of t dt. What is here? Antiderivative gives me the function itself, x of t, and its indefinite integral plus constant. Now I know how to find the position of the object. If velocity is given, the position of the object is equal to integral, indefinite integral, vx of t dt. And again, I will skip this constant because this indefinite integral will generate arbitrary constant that I will find from my initial conditions. So those two are definitions 1 and 2. And we added formulas 3 and 4 that we derived from our definitions. Those are the formulas that we will be using when we solve one-dimensional problems on kinematics. Before we start solving any problem, let's consider one very special case. I want to consider a case, and I will change color for that. I will switch to, let's see, what is a very different color here. Will this be different? Hopefully, yes. I will consider the case when, oh, very close, doesn't matter. I will consider the case when acceleration does not depend on time. Very specific case. Acceleration is constant, which means that a sub x is constant. It does not depend on time. Is it a reasonable assumption? Yes, we can have a car that is moving with constant acceleration or a train that are moving with constant acceleration. Now what my task is, I will derive velocity and position for these cases, for this specific case when acceleration is constant. Which formulas will I use? I will use formulas 3 and 4. If acceleration is given, how to find the velocity? I use formula 3, v sub x as a function of time is integral. To emphasize that this is constant acceleration, let me add c. C will stay for constant. So it is acx right here dt. Since this is constant, I take it out of this integral. Integral dt is t plus arbitrary constant. Every time I generate different constant, I just write it the same way. Now, how to find this constant? Oh, something has to be given. For example, it is given to me that velocity at time moment 0 was equal to specific number that I will call v naught x. What is v naught x? That's a number, naught here or 0 here, emphasizes that this is a specific number, 5 meters per second, whatever. Now, I will find the constant. What is v sub x at that time moment 0? Well, from my formula, I put time moment 0 here. This guy is 0. And then plus constant. At the same time, that was given to me that at time moment 0, the velocity was, projection of velocity was v naught x, 5 meters per second. I'm ready to write the formula for velocity for this specific case when acceleration is constant. I will put it here. So now, borderline, we cannot cross it. It is acceleration is constant, or it is equal to, in this case, a cx, where c emphasizes that it is constant. So, this is wrong. Why? Because I have vector on the left and I don't have vector on the right. Let me add here unit vector I, and then problem is solved. Or I just say that axc is constant. That's what we need. Okay, great. Where we are, right here, vx at any time moment. For this specific case, I still don't like it. I still don't like it. We don't need vectors. So just let's write that a sub x is constant. And that's it. AC, nothing wrong about what I did, but I want to rewrite it without unnecessary symbols. A constant x is constant. We have this constant acceleration. Then what is Vx as a function of time? Okay, it is a cx component times t plus constant, which is v naught x, initial velocity x projection of initial velocity. What is the position now? I want to find the position. Can we do that? Okay. Now I know the velocity at any time moment. I'm ready to find the position. I will use formula number 4 for that. How will I use it? Easy. I just will bring this formula here, and let's see what happens. Integral, indefinite integral. Now I rewrite this. This is constant. We remember that. T is a variable, and v naught x is a constant. It's a given number. And then dt. We cannot forget dt. We integrate with respect to time. I take this integral axct dt first. What is it? This is constant. I take it out of integral. And then integral t dt gives me t squared over 2, right? Okay, plus this is constant initial condition, something that was measured, v naught x t. Remember, it's indefinite integral. We have to generate arbitrary constant, which will be different than this one. We need to find it. How to find it? Something has to be given about the initial condition. So imagine that they tell us that at time moment 0, they measured x, and it happened to be, we will call it x naught or x0. This is a constant, okay? So now, what is x at time moment 0 according to our formulas? It is x at time moment 0. Time moment 0, this guy is 0. Time moment 0, this guy is 0. What is left? Constant. Okay? And at the same time, they told us that at time moment 0, x was 0. X naught, not 0. What did I say? X was x naught. Now we are ready to write x at any time moment for this specific case for constant acceleration. What is it? It is at squared over 2, ax projection of this constant acceleration. I keep c to emphasize over and over and over again that we can use this formula just for this specific case. AC t squared over 2. This is this guy, plus v naught x times time, and plus constant, which is x naught. Oh, look at this. We are making progress. So not only we wrote the definitions and we took entire derivative to find velocity and position at any time moment when acceleration and velocity are given. We also considered that specific case shortcut for us for many problems when acceleration is constant. The very last formula that I want to derive is there are certain situations when time is not given, and we want to relate velocity and position again for this specific case when acceleration is constant. To derive this formula, what I will do, I will use the definitions 1 and 2. I need to erase. Please stay with me. Give me a second. Let's use formulas 1 and 2 for this specific case, constant acceleration. I will take equation 1 and I will divide it by equation 2. What will we have then? If I do that, then on the left, I will have ax, and I remind us that this is constant acceleration, divided by vx of t. And this is equal to this guy divided by that guy will give us dvx over dx. Now, for a change, let's use definite integrals. Let's integrate from time moment 1 to time moment 2. I take definite integral. No, not yet. Before I take definite integrals of both sides. This doesn't look good. I will multiply both sides by dx, and I multiply both sides by v. What will I get? I will get ax c dx, and this will be equal to vx of t dvx. And now I will integrate it from t1 to t2, definite integral. At time moment t1, let's assume that our object was at the position x1 and its velocity was equal to v1. And at time moment t2, the position of the object was x2 and velocity of the object was v2. Okay? What do we have on the left-hand side? Remember, acceleration is constant. We do it for this specific case. Integral dx is just x, and I plug in the limits of integration, which will bring me to x2 minus x1. This is the left-hand side. What do we have on the right-hand side? Look what I have here. Variable dvx. So it is Vx dVx like x dx. What is the result of the integration? It is Vx squared over 2. And the limits are V1 to V2. We need to plug in the limits. I will write here, keep going here. What do we have? We have 1/2, this 1/2, and then upper limit, V2. I don't like it, and I will tell you why. Why not? What I skipped here, I skipped x. I skipped x here, and I skipped x here. Let's add x. And then it looks much better because we remember that all this motion is in one dimension. Now it looks good. V2x, we remind ourselves it's along x squared minus V1x squared. I like it better. Or I rewrite it, V2x squared, final velocity, minus initial velocity squared is equal twice, 2 comes here. And then ax, projection of constant acceleration on x, x2 minus x1. I add this last formula here to these formulas with constant acceleration. We have v2x squared minus v1x squared is equal to 2ax, again for the constant acceleration, and then x2 minus x1. This C emphasizes that this is the case for constant acceleration. We derived all these formulas. Now I want to make a point. Do you remember that somewhere, I don't know, 2nd grade, 7th grade, somewhere, they told us that the distance is velocity times time. How does this fit in all this? Does it? Yes. Let's look at it. So, imagine that the object moves with constant velocity. Constant velocity now, not only constant acceleration. In this case, acceleration is 0 because velocity is constant. How do I know? Because acceleration is rate of change of velocity. Velocity is constant, rate of change is 0, so v naught x is constant and ax is 0. I'm looking at this formula now. What do I have? This guy is 0 because acceleration is 0. Let the object start at the origin, initial position is 0. Then what do we have? For this case, we immediately get that position of the object is just constant velocity times time. Exactly what they told us many years ago. We just need to understand that this works for the case when acceleration is 0 and velocity is constant. Object moves with constant velocity. Imagine that a car, a toy car, is moving with velocity, constant velocity, that is 6 meters per second. So I'm given that car's velocity is 6 meters per second. Constant velocity means 0 acceleration. And I'm given that the car is moving during the time period, delta t, 8 seconds. I want to find the position of the car at 8 seconds. What is it? This guy is 0. This guy is 0. I have constant velocity, which is 6 meters per second. This guy times time, which is 8 seconds. 6 times 8, 48 meters. We just consider one specific case. Constant velocity, which means 0 acceleration, and we found position. Now we have all these formulas, and we are ready to solve the first problem on kinematics.